It's been a really exciting day of conversations, very broad conversations ranging from exoplanets to supermassive black holes. So very stimulating to be able to talk with you about all of these topics. As Matteo mentioned, I'm at Yale and I run the Yale Astro Machine Learning Group. The thing that I'm going to be talking with you about today is, I would say, not our normal science. The science we do is actually, in fact, a lot more normal science. What we try to do in the YAML group is confront big theoretical data with big observational data. And so we look at large-scale surveys like Gaia and TESS and other such things, mostly looking at observations of variable stars and try to interpret them using large-scale simulations, MESA, gyre, FIRE, et cetera. And so there's a few different broad categories that we're usually working on. A large number of us are working on astroseismology, so study of pulsations in stars. We're also trying to connect those observations and interpretations of stars to their galactic context, looking at the Milky Way and the Milky Way's dwarf galaxies. We're looking at early universe physics, like the formation of the first stars and their chemical feedback and influence on their host galaxy. And of course, doing some machine learning to unite all of these, for example, by accelerating the numerical simulations and using them to aid in the interpretation of the observations. But I'm mostly not going to talk about any of that stuff today. Instead, I'm going to talk about, I would say, a fun line of research that started, I have to admit, out of boredom and COVID. I was just playing around and stumbled across a new way of making stellar models that I think turned into like a fruitful line of inquiry. So I'm going to be talking to you today about 4 hypothetical classes of stars, none of which might actually exist in reality in our universe. Some people are convinced that they do exist. I myself am skeptical and think that we shouldn't believe that they exist until we get evidence. But in order to get evidence, we need to know what to look for. And so in order to figure out what to look for, we've made models of these different types of hypothetical objects. And today I'm going to present to you these models and the unique observational predictions that they make, so that hopefully we might be able to go out and say these things really are real, or rule out their existence. So let's start with the Hawking stars. So this first story begins with the problem of dark matter. We've known now for about a century that most of the mass in the universe is invisible. But the nature and origin of this mass remains unknown. One idea is that the dark matter could be comprised of black holes. And this is an alluring idea because black holes are dark matter. They're one component of the dark matter. We just don't know if they're all of the dark matter. If you do some accounting of the ways in which we know black holes exist, we see that they fall short. If you look at the Milky Way, comprised of 200 billion stars, and you do the arithmetic on the generations of star formation that has transpired, we know that out of all the massive stars that have been produced and have ended their lives as black holes, that should give the Milky Way a population of approximately 100 million stellar mass black holes. We know that can only comprise less than 0.1% of the dark matter. Similarly, if you look at the supermassive black hole at the center of the Milky Way, that contributes at most a 0.010% of the dark matter. And so if we want black holes to make up all of the dark matter, we need another channel to produce them in great abundance. So Stephen Hawking came up with an idea back in the 70s that could potentially produce this enormous population of black holes that could potentially explain the rest of the missing mass in our galaxy and other galaxies. And this idea is the so-called primordial black holes. In the immediate aftermath of the Big Bang and the radiation-dominated era, you could have locally overdense regions of space-time that collapse directly into an enormous population of potentially very low mass black holes, but also potentially much more massive black holes as well. It's interesting to recall why Hawking thought of this idea. He was motivated by the, at that point, unresolved solar neutrino problem, which was that the theory of stellar evolution had emerged, that the sun gains its energy through nuclear fusion reactions in its core. As a byproduct of these fusion reactions, neutrinos are generated, they free stream out, and then they can be detected on Earth. But upon their detection, the counts of these neutrinos were much lower than predicted by stellar evolution theory. And so Hawking suggested, and he was no stranger to wild speculation, that perhaps if the sun had captured a primordial black hole at its core, the accretion onto that black hole could serve as the power source for the sun. And that's because black holes are the most efficient known engines in the universe, much more efficient than nuclear fusion. And so if a third of the sun's luminosity was coming from fusion reactions and the other 2/3 were coming from accretion onto a compact object, that would solve the solar neutrino problem. We now know that the solar neutrino problem has been solved by other means. And so this suggestion kind of fell out of favor. But primordial black holes remain one of the potential candidate solutions. What is this sound? Is that me? Is that my own feedback? Oh, perhaps we can mute the mics on Zoom. Primordial black holes remain one of the candidate solutions to the dark matter problem. And they're attractive because they don't require any modification to the known laws of particle physics. Standard model seems to be working pretty well. So this is potentially one avenue that could solve it. Although, of course, it's possible that there are multiple components to the dark matter problem, that there's not just one channel or one type of dark matter, just like there's not just one type of baryon. So it could be that the universe made some small number of primordial black holes. It could be that the universe made an enormous population accounting for all of the dark matter, or it could be that the universe made none of these at all. Constraints on their masses still leave open the windows of asteroidal mass primordial black holes, sublunar mass black holes, and intermediate mass black holes. These could still exist and are not ruled out by observations. This is a topic that's been gaining popularity. In Hawking's day, it didn't have that much attraction, but in recent years, the number of papers on primordial black holes has taken off considerably. So people are out looking for these things, and we thought maybe stellar physics has something to say on this topic. So how massive are these? Well, one thing that's just fun to remind ourselves is that Hawking's arguably greatest contribution to science is the idea that black holes evaporate over time, right? Probably the last event that will happen in the universe is the evaporation, the final evaporation of the most supermassive black holes. It'll take something like 10 to the power 1,000 years to occur in the far distant future. How did he come to that idea? It was actually contemplating the quantum mechanical properties of these primordial asteroidal mass black holes. So that's one argument, that even if these things aren't real, their physics is still interesting, and studying their physics can lend us insights into other problems. And we're going to see this come back again at the end. But anyway, just to give you an idea of the mass that these things possibly could have, the very lowest mass primordial black holes that the universe could have produced would have evaporated by now. I like to express things in terms of solar units because, spoilers, I'm going to put one of these in the sun and see what happens. So at 10 to the power minus 18 solar masses, this is the black hole evaporation limit. By the time the sun has formed, all primordial black holes less massive than this would have evaporated. And then between that mass and the mass of the sun, you have a possible population of primordial black holes that could exist to the present day. And so we're talking about something like the size of Saturn's moon Hyperion floating around. And you know, if these things supply the dark matter, then there's something like 10 to the power 30 of these mass objects in the Milky Way, which of course gives the possibility that they might have some interaction with the stars in the Milky Way. Now, if these things are whipping around the Milky Way, they're doing so at a pretty similar velocity that, let's say, the sun travels around the Milky Way. So the probability of encountering one is pretty low. And furthermore, their sizes and therefore their cross sections are extremely tiny. In fact, if one encountered the present sun, it would just pass right through it like a bullet. The sun has no chance of capturing a primordial black hole in its present state. We might see it if it happens because it might excite transient oscillations as it goes through the sun, but it's not going to stay inside of there. On the other hand, during the formation of the sun, when the sun had a time variable gravitational potential, that gives the opportunity to capture a primordial black hole upon formation. Nick Esser did some very interesting calculations a couple of years ago where he reasoned about how many such stars in the Milky Way may have captured a primordial black hole upon their formation. And he came to approximately 1 in a million stars in the Milky Way. So a priori, does the sun have a primordial black hole at its core? Almost certainly not. Even if these things comprise the dark matter, there's only a 1 in a million chance that the sun was one of the, I guess it depends on your perspective if it's lucky or unlucky, but one of the ones that captured these upon formation. But still an interesting question to study. What happens if you capture one of these things? Do these stars evolve differently? Do they have unique signatures? And can we use such stars as dark matter detectors to either confirm that primordial black holes make up some or all of the dark matter, or finally rule out this proposed class of dark matter candidate? And so, yes, during formation, a star could capture a primordial black hole. The black hole would make its way to the center of the star. I mean, most realistically, it would probably orbit around the center of the star, but we're going to ignore those details. And then it would accrete the star. And the question is, what happens then? How does that affect the evolution of the star? And if this thing is an efficient engine, then it should, and the luminosity can get out, it should provide some feedback for the rest of the stellar structure. For example, driving convection in a zone outside the cavity from which it's accreting. So this was a nice figure prepared by my friend and collaborator Warwick Ball, fellow MESA developer, who did actually early numerical modeling of quasi-stars that we'll get back to at the end. So it's nice that I get to show off his beautiful diagram. So as I just mentioned, we modeled this using MESA, Modules for Experiments in Stellar Astrophysics. This is a software instrument for studying stellar evolution. There are several MESA developers in the room, E.B. Faraj. You probably, I guess people here know about MESA. The Flatiron's been a great supporter of MESA. Matteo Cantiello is here. Yeah, there's been this great hire of a research software engineer who's Philip Mox, who's been helping support the project for the last a couple of years. That's been fantastic. It's one of the most visible open source projects in all of astrophysics. So I guess most of you have either used it or at least heard of it. So just to whet your appetite, because I know some people do stuff that's other than stars for some reason. This is a typical evolutionary track of MESA that reproduces the ordinary evolution of our own sun. So here's the birth of the sun, here's the present sun. In the future, the sun's going to turn into a subgiant star and eventually inflate into a red giant and incinerate the Earth. We normally model this by solving the equations of stellar structure and then supplementing this with evolutionary equations for nuclear reactions and for transport of chemical elements and other such things. So these are the normal stellar structure equations that MESA solves and allows you to simulate the lifetime of a star. But what we are going to do is change the boundary conditions that MESA solves. Instead of saying that there's no mass at the center and there's no luminosity at the center, what we've done is we've changed the interior boundary conditions to have some enclosed mass and then a subgrid model for the operation of the primordial black hole. So whether or not luminosity comes out from this center point, how this mass grows over time, et cetera. So modeling the accretion physics of the black hole being embedded at the center of the star, this then allows us to simulate how such an object would evolve over time and what its observable properties could be. Now, in order to do this, we have to assume an accretion model, right? We have to say how this black hole will grow over time and whether or not it can supply luminosity. There's a quote here from Kip Thorne, who a lot of people know him from Interstellar, but this crowd should know him from winning the Nobel Prize and his great scientific work. He made a point in the 1980s, which I think is still somewhat relevant today, which is that there's a number of unresolved issues about spherical accretion of black holes. We don't know if a black hole embedded in something like the sun, if it would be something like an all-you-can-eat buffet where the sun just falls in, or if the accretion process is very slow. So that's basically what he says in so many words. And so as someone who is not a black hole physicist, I decided to talk to lots of black hole experts and ask what the reasonable range of accretion models are for a primordial black hole embedded in the sun. And so we just decided to implement different accretion schemes and study what the different outcomes are. And so here are a couple of them. You can have Bondi style accretion and an associated luminosity. So this is where the mass grows with the luminosity goes with the black hole mass squared. You can also have Eddington style accretion where the luminosity goes with the mass, et cetera. And so we try to bracket the range of physical outcomes. I've been having very fascinating conversations here today with some people like, was it Orr, right? Orr and Matteo, who are trying to study this project, the accretion in more detail. I'm really happy there's follow-up on this work trying to actually simulate the accretion. Like I said, even if these things aren't real, the physics is interesting, I think worthy of study in their own right. So using proper tools, GRMHD simulations to actually model the growth of these things. Anyway, we implemented subgrid models, subgrid physics, accounting for these different growth schemes. And I'll show you one of the outcomes. So this is a Kip and Hahn diagram showing the ordinary growth of the sun. So this is the birth of the sun. This is the present age of the sun. And each vertical slice here is the internal structure of the sun. So you have the mass coordinate right here. So you see in the core of the sun, fusion is ongoing. A very small layer of mass is transporting energy convectively. That's what these hashes indicate. If we look in terms of radius, it's the same diagram. The core has nuclear fusion, and the outermost 30% of the sun is transporting energy by convection. This is a normal evolution of the sun. When it finishes central hydrogen fusion, it will leave behind an inert, non-burning helium core and will continue fusing hydrogen in a shell. The convective envelope will deepen and the photosphere will expand. The sun will turn into a giant star. The situation changes quite dramatically if you put a black hole in the center of the sun. Here you see the growth of the black hole. So in the beginning, according to this subgrid physics accretion model, the growth is very slow at early times. And this is due to the Bondi style accretion being inefficient at small masses, but at a certain point, it starts to take off. Now, here's something quite interesting happens, which is that in these simulations, the black hole is radiatively efficient, which means that as it's accreting mass, it's also releasing an enormous amount of luminosity, and that luminosity serves as a power source for the star, just as Hawking suggested. That drives the star to become fully convective. And in fact, you still see it still puffs up the star into a giant. Meanwhile, because the luminosity from the black hole is so intense, the nuclear reactions shut off. Again, as Hawking predicted, you wouldn't supply as much luminosity from fusion if you can supply it from accretion onto the black hole. So you would see you see the nuclear reactions shutting off as the black hole becomes the engine powering the star. Yeah, and so you get a star that has a fairly sizable black hole, although of course it's much smaller than the known black holes, in its core, embedded in a stellar envelope, and that envelope is fully convective. So here's again the evolution of the sun if it had been born about a primordial black hole of different masses. So here you can see the normal evolution of the sun as it turns into a giant. And if it had been born about a black hole, it will then prematurely end its normal evolution and make this diversion to low temperature and then eventually to high luminosity. You notice that the place that it ends up is to the red of the red giant branch. These are the so-called red straggler stars for which ordinary single star evolution does not provide a recipe. You also notice that these things, at least according to this accretion model, these objects are long-lived. I mean, this thing lives for many billions of years as a red straggler star. And yeah, I suggested we dub these things Hawking stars in honor of the man who first thought about the sun capturing one. And one thing that's interesting, kind of suggestive, but not, in my opinion, totally compelling, is that we do see a small population of red straggler stars. Now, accretion onto a black hole is not the only avenue that can produce red stragglers. There are also binary channels that make red straggler stars. But I also think stellar pulsations provide a unique probe that will tell us if these stars actually host a compact object in their interior. Because normally, when you produce a red giant star, missions like Corot and Kepler have revealed that these stars pulsate with a very beautiful spectrum of so-called mixed oscillation modes, where the G modes that are trapped in the core couple with the P modes in the outer envelope, and you get mixed oscillation modes. And that's because you have a radiative interior where G modes are unstable. But if your stellar structure is entirely convective, there are no G modes because G modes are the opposite of convection, right? One is runaway buoyancy and the other is an oscillation in buoyancy. You would get a spectrum of pure acoustic oscillations in a red giant star, which hasn't been observed. And so if these things are in fact Hawking stars, they would be red giants that, unlike normal red giants and unlike these binary channel red giants, they would show evidence of having no core through having pure pressure mode oscillations. So astroseismology provides a route to potentially confirming the existence of Hawking stars and therefore the existence of primordial black holes, or falsifying them if we can observe enough of these red straggler stars. Remember, this scenario is rare, 1 in a million in the Milky Way. We'd have to observe enough of them to say that this doesn't happen. Now, one caveat, of course, is that this depends on the subgrid accretion model that we've adopted. This was assuming that the radiation is efficient and therefore can serve as a power source for the star. If, on the other hand, the photons are trapped and dragged directly into the black hole, then you would expect a very different situation where the star just falls into the black hole, in which case we have a different prediction. The stars would just disappear from the night sky on a very short time scale. You would see a star and then you wouldn't see it anymore. There would be a population of disappearing stars. Intriguingly enough, there does seem to be of order 100 M-dwarf stars that have vanished from the night sky, but this will require further study to know what's going on with these stars. So that finishes up my first story that I wanted to share with you, which is this regarding this hypothetical class of star known as Hawking stars, which are potentially giant stars powered by a primordial black hole at their core, and the possibility of detecting them both through their position in the HR diagram and then ideally through their unique seismic signature of having pure acoustic oscillations, unlike normal red giant stars, or alternatively, causing stars to simply vanish. Now I'm going to move on to, I would say, a more general class of dark matter. And I call these very generically the dark matter stars. Here we wanted to investigate in detail. Primordial black holes are one type of macroscopic dark matter, but there are other types as well. For example, strange quark nuggets that Ed Witten came up with. These things, if they got embedded in the core of a star, they would not serve as a power source, but they would still be, some kind of a lump of dark matter in the core of the star. And so the question is, using similar reasoning, for example, astroseismology, can we find if these things have a compact core that's non-luminous? So it could be a primordial black hole, but it could be something else as well. So just a more general class of dark matter. And for this, we decided to study the sun specifically and in great detail. So here are evolutionary models of the present sun with a variable amount of dark matter in the core. And it's the same trick as before. We put a point mass in the center, and this time it's just non-luminous. It's truly dark matter. And so here you can see the internal structure of these models. This is the center of the model, and up here is the surface of the model. And we're putting in variable amounts of dark matter inside the center of the sun and evolving it to the present day. So all of these models reproduce the present day observed properties of the sun, the bulk properties, same mass as the sun, same age as the sun, luminosity, radius, metallicity, all the same. They only vary by how much dark matter is in their core. You can see the density structure of these models. A model with very little dark matter in its core has the same density structure as a model with none, but as you ramp it up, you get a great density gradient in the deep interior of the sun. Because these are evolutionary models, we can look at how this has affected the nuclear burning inside the sun and therefore the chemical abundances in the deep interior. And you can see, for example, that if you have a very massive dark core in the solar center, then you'll have a correspondingly very large helium abundance. And this is because if we look at the channels of nuclear burning in the present sun with different dark core masses, a massive dark core causes your PP fusion reaction to occur off-center and greatly enhances your CNO fusion reactions. And this goes back to the great density gradient that these dark core models have. So the main energy output, instead of being almost entirely fusion PP powered, as in the normal sun, you would get great contribution from CNO, and that would change the helium abundance in the solar core after 4.5 gigayears of evolution. A very interesting thing that happens in these models is that if you have a compact mass in the center of the sun, you will greatly enhance the gravitational potential around that mass. That means that the metals that are slowly sinking into the sun, this mass can accelerate that process, transporting metals more quickly to the center. And so you see, for example, in this dark core model, the metal abundance of the solar core goes up dramatically. This is simply gravity acting on the heavier elements more than it does on hydrogen, for example, creating mean molecular weight gradients. So what are the observable consequences of this? Well, first thing is that because the nuclear energy generation in the sun has changed from being dominated by the proton-proton chain to the CNO cycle, you change your CNO neutrino flux. So in gray here is the 1 sigma detection from Bork-CNO of the CNO flux. And you can see that, okay, it's not very discriminating actually. The most massive dark core model considered is like only maybe 2 sigma or so away from the measured CNO flux. But the PP flux is much more discriminating here. Already based on the measurements of the proton-proton neutrino flux, we can rule out the most massive dark core model. So we know from this that 1% of the solar core is not dark matter. Maybe already an obvious fact, but probably good to check. A more discriminating tool is the acoustic oscillations of the sun. So since the 60s, we've known that the sun hosts a rich spectrum of acoustic modes. This is a Dopplergram of the solar surface. And this pattern you see is due to a rich spectrum of oscillations. We can detect thousands of oscillation modes in the sun. They're extremely low amplitude, which is why it wasn't until the 1960s that they were first discovered. And the precise measurement of the frequencies of these oscillations reveal the solar interior structure, which these measurements confirm in broad strokes, the theory of stellar evolution, in contrast with the solar neutrino problem. Already at this time, when the solar neutrino problem was going on, solar astrophysicists were convinced that the problem was not with the model of the sun, because the helioseismic structure of the sun is in such good agreement with evolutions of stellar evolution theory that rely on nuclear physics calculations. And so they show us that the sun has a nuclear burning core and then radiatively transports energy, and then the outermost 30% of the sun is transporting energy by convection. And it's precisely this turbulent convection in the outermost layers of the sun that stochastically excite the broad spectrum of acoustic oscillations that we can see in the solar data. I have some music if you want to hear it. You want to hear what the sun sounds like? This might be loud. Oh, it can't load. Well, can I sing it? It doesn't sound beautiful, and that's because it's not very harmonic, it's a bunch of random frequencies. Imagine hitting like every key on the piano at once. Okay, but this is what the power spectrum of the sun looks like. Now, with these measurements, we can contrast the actual structure of the sun as revealed through helioseismology with the structure of the sun given by solar evolution models. And this has been done since the 1990s. I did my first postdoc with JCD, who fairly recently won the Kavli Prize for this work of inferring the structure of the sun using helioseismology, and then using those measurements as a test of stellar evolution and solar physics. Okay, so the game here is that we evolve a model using stellar evolution theory to the present age of the sun, having the present surface properties of the sun, and then predict the oscillation frequencies of that model, and then contrast those frequencies with the observed frequencies. And then this allows us we can then invert the data to figure out where inside of the sun the model agrees or disagrees with the actual sun. So here I have the difference in the internal sound speed profile between the sun and evolutionary models. And the sound speed this is the ratio of pressure to density inside the sun. This is the relevant quantity. This is the thing we can measure the best because, again, these are acoustic oscillations. So they vary with the local speed of sound as it goes throughout the sun, which varies from like 10 to the power 7 centimeters per second down to like, of order unity at the surface. So great contrast in the sound speed profile inside of the sun. Back in the 90s, JCD was able to compute solar evolution models, making different assumptions about the physics that operate inside solar models and show that the solar observations can distinguish these models. In particular, it's exactly this thing I was just talking to you about with the gravitational settling of elements. The heavy elements will slowly sink into the sun. These are the models labeled diffusion. And you can see that each of these models agrees better, is closer to this 0 line than the model that doesn't have this settling of elements into the interior. So there's a few things that are worthy of note here. One is the scale, right? The difference between the structure of the actual sun and solar evolution models is less than 1%. By astrophysical standards, that's like a home run, right? I mean, nailed it. But you can see that it's not in perfect agreement. There's no perfect model at 0 here. And that remains the case to this day. Solar evolution models still cannot fully reproduce the actual structure of the sun. This has been a problem for decades. And no one really knows exactly what the problem is, nor how to solve it. And so again, we're looking at the difference in internal structure between the sun and the solar evolution model as inferred through the sun's normal modes. And again, you see differences of order 1%. People have made different models where they've made different assumptions on the models. None of these models are able to fully reproduce the structure of the sun. In absolute terms, the agreement's great. It's less than 1% difference. But in statistical terms, this is something like a 60 sigma difference between the solar model and the solar observations. So there's something wrong with our solar evolution models. It's at a level where we think the models are at least broadly qualitatively correct. I mean, it's better than 99% right, but we can tell the difference. Okay, maybe you see where this is going. We return back to putting dark matter in the sun. First of all, how sensitive are the acoustic modes? Well, if we put dark matter in the core of the sun, we can see how much we perturb the frequencies of the radial modes of the sun, right? And that's because it's bouncing off of a different inner boundary, right? And also like the amount of mass that's oscillating is different. And we can compare that with the uncertainty, the precision with which we can measure the solar oscillations. If the sun has a dark core that's less massive than about 10 to the minus 5 solar masses, we'll never be able to tell because it'll be hidden in the noise. But if it has a more massive one, then its signature would show up in the solar oscillations. This is also showing the acoustic oscillations of the sun probe the outermost layers of the sun. We can only really measure to the innermost 5% or so of the sun using helioseismology. That's where these measurements come in, measurements of the sound speed profile. But of course, it's these inner regions that are really diverging if the sun actually has a dark core. And now I compare the frequencies of these dark core solar models to the actual frequencies of the sun. And something interesting happens around 10 to the minus 3 solar masses. Caveat, of course, being that we've added a free parameter, so we should expect some improvement. But if you look here in white, this is the normal solar model compared to the observations of the sun. So you see frequency differences, right? And if you put in a 10 to the minus 3 solar mass, just nugget of dark matter in the core of the sun, you improve the agreement between the model and the observations. And this gray band here shows the observational precision. So it's improved. It's improved by about a factor of 10, but it still doesn't explain the full solar model. And then if we look at the differences in the internal sound speed profile between the sun and the solar evolution model, again, normal solar model in white, you see these large differences of order 60 sigma or so. And if you put in a 10 to the minus 3 solar mass model, at least in some regions, you get much better agreement. Now, let me be clear. I am not suggesting that we have found dark matter in the sun. It does seem that the model is improved when we add this free parameter. This allows us to ask the question, why has the model improved? And I told you what adding the dark matter does, right? It increases the gravitational acceleration. It causes the metals to sink to the center. It gives the sun a heavy metal core. Now, why might that have improved the model? Well, there are some star formation theories that suggest that the sun may have been born with a heavier core rather than a chemically homogeneous structure. Maybe the sun first accreted metal-rich gas, and then the gas it's accreting, the metals from that got drained into forming the planets, because we have a metal-rich Earth and Jupiter and so on, and then the remainder of the accretion was metal poor, and so that would give the sun a metal-rich core and then a metal poor exterior. Such a model might also improve the agreement with helioseismic observations, and maybe we're only rediscovering that model through a roundabout way using dark matter. What could distinguish these? Well, in the future, we hope to measure not only P modes in the sun, but also these G mode oscillations. G modes will allow us to resolve the solar core. If there's a hunk of dark matter in the center of the sun, then that will increase the buoyancy frequency in the center of the sun, and that will change the spacing of the G modes inside of the sun. And so here, again, in white is a normal solar model, normal period spacing. Even if it's less than a millionth of the mass of the sun, the G modes would dramatically be changed if there's dark matter in the solar center, because it's precisely this boundary that they'll be bouncing off of. So future measurements of solar G modes will be a great aid in distinguishing if these dark matter stars are actually real. Now, again, like with the primordial black holes, if there's actually a big lump of this thing that falls into the sun, we might expect the capture rate to be similar to the PBH case. So maybe, again, something like 1 in a million stars would have something so massive, or even less common. So again, I'm not holding my breath that the sun has a dark matter core, but if it does, future G mode observations would allow us to detect it. Yeah, okay. Summary for that part, and I have to speed up dramatically. So solar evolution models are potentially laboratory for dark matter. Solar neutrinos provide very weak constraints. The acoustic oscillations of the sun provide stronger constraints. In the future, we hope solar G modes will provide the strongest constraints. And somewhat surprisingly, a solar model with a 10⁻³ solar mass dark core improves the solar model by something like a factor 10. Okay, I'm probably gonna have to skip through some stuff. Thorne-Żytkow objects are fun but uncertain outcomes of binary stellar evolution. Let me take you through this diagram. If you have a pair of massive binary stars, the more massive one evolves first, undergoes Roche-Lobe overflow, and donates some mass to its companion. Then, after Roche-Lobe overflow completes, the primary explodes, turns into a neutron star. Then the secondary expands into a giant. That neutron star can in-spiral to the center, forming a Thorne-Żytkow object. Maybe. We don't know if these things are real. We don't know if the neutron star would instead unbind the envelope. There's some simulations suggesting that these things can actually form, and there's some that suggest that they never form. And so, similar to the other cases, we modeled this using MESA. And by we, I specifically mean Rob Farmer, who has unfortunately left astrophysics, but led this very nice paper 2 years ago on the evolution of Thorne-Żytkow objects with MESA. And here you can see how they evolve in the HR diagram. You can see that they go to lower temperatures and lower luminosities over time. And my particular interest is in the oscillations. So we studied the frequency spectrum of these things. We see that they have extremely long periods. This is the fundamental period and first and second overtone periods. There was a candidate TZO, HV 2112, but we can see that the oscillations in this candidate TZO don't match the evolutionary models. And so we think it is not a TZO. One thing that's really cool about these models is that if you have a neutron star embedded at the core, you get very intense nucleosynthesis. Rob needed to compute these models using a 400 isotope network. Pretty crazy. At the base of this model, unlike in the Hawking stars, for example, where fusion ceases, here the fusion becomes so much more intense and you produce rare elements such as titanium. And so if you can see a red supergiant star that pulsates with this spectrum of oscillation modes and has titanium oxide in its atmosphere, then that would confirm that a neutron star can survive the common envelope phase of binary evolution and that these Thorne-Żytkow objects can actually grow. Yeah, I don't have much time to talk about it, but I met Kip Thorne like a week ago. So this is a Thorne Bellinger photo. There might be 5 of these TZOs in the Milky Way. And so we'd like to look for them and look for these unique signatures to find out if these things are actually real. Okay, the last thing I would like to talk with you about today are the quasi-stars. So recently, James Webb has revealed a very interesting population of objects known as little red dots. And a lot of different explanations have come forth to what these could possibly be. These are between redshifts 3 and 10. So they're extremely distant early universe objects, maybe in the first giga-year after the Big Bang. They don't look like AGN. They don't look like normal galaxies or anything. People don't really know what they are. Simultaneously, James Webb has observed a population of very high redshift supermassive black holes. The question is, how could the universe have produced supermassive black holes so early? Quasi-stars allow us to solve 2 birds with 1 stone. A quasi-star arises in the early universe. You have the first epoch of star formation, so there's no metals in the universe. Now, with these population 3 stars with no metals, we expect them to be massive, maybe of order hundreds of solar masses, but stopping there. But if you have a nearby galaxy that's providing LW radiation, that can prevent the cooling of this protostellar gas, which would then enable these masses of the first stars to grow to perhaps 1 million or more solar masses. If that's the case, then the core of this firstborn supermassive star could collapse directly due to the GR instability, forming a stellar mass black hole at the core of a supermassive star. And so again, we find ourselves in this first scenario that I talked about. We have a star with a black hole at its core. And so we decided to model its growth. So this is work that was led by my graduate student, Andy Santorelli, and helped out considerably by E.B. Farage, who I'd like to say is like the most useful person on the planet, particularly with regards to MESA. You probably all know him from the MESA Users Forum. He's probably helped half the people in this room with their various problems. So I just want to give him appropriate kudos for being such a generous community member. So we modeled the evolution of these quasi-stars. So this is how such an object evolves. This is 1 million solar mass quasi-star. So the envelope is 1 million solar masses. It doesn't matter where you set the black hole seed as. This could be like, let's say, 5 solar masses. But it's important to keep in mind that this is a direct collapse black hole in the early universe. Here you see that it initially goes through a very brief contraction phase on the Kelvin-Helmholtz time scale. So this only lasts like, fractions of a mega year. And then it lives a long-lived, maybe 20 mega year phase where the black hole between, the black hole is then about 10% to 50% of the total stellar mass of the object. So this black hole is already 10 to the 5 solar masses when it hits this point. These things are extremely low temperature and ultra low surface gravity objects. One thing I'd like to add is while we were preparing this paper, Matteo and his student and group of collaborators actually worked on the same problem at the same time and produced other very nice simulations of quasi-stars. And so similar to the diagrams I showed in the beginning, here you can see the growth of the black hole under some assumptions of the wind scheme. And you can see that this black hole, this quasi-star grows to something like a few times 10 to the 3 solar masses. Here we've made a grid of quasi-stars of varying masses. Our most massive case gets up to 1 million solar masses. And one thing that's interesting is that they form this Hayashi-like track. And that's because the outer envelope is fully convective, just like with the Hawking stars. And yeah, Matteo made this point earlier, which I'll repeat, which is that although the Hawking star scenario was fun and maybe not real, just like with how Hawking working on primordial black holes led him to work on the Hawking evaporation, us working on primordial black holes led us to quasi-stars, which is maybe a nice little gift inside of it. Here we can see the lifetimes of these objects. They live for about 20 mega years, which means that they could plausibly explain every little red dot. You can fit them in to those observations. You can grow these supermassive stars. The timescales are right. Yeah, maybe I'm burying the lead a little bit. We compare the spectra of these quasi-stars to the observed James Webb spectra of little red dots. Now, one caveat I have to make here is that if you look at our atmosphere grid, right, we just adopted some LTE atmospheres from Atlas 9 because we don't make our own atmospheres, so we just grabbed some readily available ones. The Atlas grid doesn't give us zero metallicity spectra, right? Their lowest metallicity is 10 to the minus 5, and they don't give us ultra low gravity spectra either, right? They cap out at log G of 0, which, fine for most people, but we're working with quasi-stars. So we had to look at the most massive quasi-star with the lowest surface gravity, and we had to settle for something that had non-zero metallicity. And these atmospheres are LTE, which means that they're not going to accurately produce emission features. So we can only hope to reproduce the continuum spectra of these little red dots. But if we look at them, we can reproduce the low far UV emissions as well as the high near infrared emissions. We only looked at 2 little red dots, like MOMBH star 1, for example, and this other one. But we can reproduce the continuum spectrum fairly well. There are, of course, areas where it disagrees. These emission features are not something that our atmosphere models are currently capable of producing. We need NLTE atmospheres at ultra low gravities and zero metallicities. It's not available in the literature. We weren't able to, at least we weren't able to find and download any of these. But the features that our models are capable of predicting, these predictions match the James Webb observations of little red dots, lending support to the hypothesis that the little red dots might actually be quasi-stars, direct collapsed black holes that accrete a supermassive star in the early universe. And if this is true, we might be witnessing the birth of the first supermassive black holes. So to summarize, quasi-stars are direct collapse heavy seed black holes. We've developed a toolkit called MESA Quest, and Andy Santorelli is the lead developer. And one thing that he's done, which I think is important, is, like I said all along, we don't know how the accretion physics should work in these models. And so Andy has made this open source tool where we can flexibly swap out different accretion schemes. He's implemented the saturated convection accretion scheme from Begelman, as well as Bondi style accretion and Eddington style accretion. On the surface, you can accrete mass because these are growing objects. You can also flexibly change the wind scheme, including radiation-driven line winds that he's recently implemented. And so it's possible to mix and match these different physics of quasi-star evolution and study the different outcomes, study the different spectra that they produce. And the kind of astonishing result is that these models reproduce the continuum spectra of JWST's little red dots. Given their lifetimes of 20 mega years, these could easily produce the entire population of little red dots, and therefore plausibly may explain not only the little red dots, but high redshift supermassive black holes. Okay, so that's what I wanted to tell you. I wanted to talk about 4 different cases where we put compact objects where they may or may not belong. The Hawking stars with primordial black holes at their cores that produce these red stragglers, or alternatively, the disappearing stars based on the adaptive accretion physics. These dark matter stars where we studied the solar structure in detail, saw that it somehow improved the solar model and produces unique predictions that will allow us to test whether or not the sun has dark matter in its core. The Thorne Żytkow objects, which are uncertain outcomes of binary common envelope evolution, and the quasi-stars, these direct collapsed black holes inside supermassive stars, potentially the first stars in the universe, which may be the origin of supermassive black holes, and they may be the explanation of the little red dots. Thanks for your attention.
Time for questions. That's so nice stuff. So we've seen little red dots, not even like redshift past 4, but also intermediate redshift starting from 0.1 to like 2, 3, and 4. So one of the things that is very puzzling is their narrow lines. When you take the optical emission line ratios, they fall in the star forming regime, but they show winds, and those winds are aging photoionized. So I was wondering if your model could actually explain this kind of weird discrepancy that we've been seeing in the observation. That'll be great.
That's a very interesting question. I'd be happy to talk with you more detail about that. I don't have an answer off the top of my head. Yeah, but thanks for that.
Yes.
So I was just wondering about your accretion models, particularly for the black holes. So if you are, so you said that they're spherical, but you might not expect them to accrete spherically, right? If the sun or star has some angular momentum, then you might expect it to form a disk.
Right.
And then to accrete and to increase the angular momentum, the spin angular momentum of the black hole at the center, which could then also, right? So like, I'm wondering, obviously, you got to start somewhere, but have you thought about the potential implications of spinning up the black hole in the center of the star, which could then trigger like a jet or something like that? Absolutely.
That's a great point. Have I thought about it? A little bit. Have I done anything about it? No. What we would need to study that in more detail is some kind of subgrid accretion model that takes that into account. Regarding the angular momentum, I mean, stars are born rotating, and even a slowly rotating star, if you have, if we take the primordial black hole case, even after a few mass doublings, you would spin this up to a maximally spinning black hole. But you could power a jet, which would rob that black hole of its angular momentum. These are very interesting topics that should be studied. I'm hoping experts like Orr can get to the bottom of those things and can provide a prescription that we can use in 1D models. Because this is 1D, we can't take into account 3D effects. Rotation itself is even challenging in 1D. Jets would be super challenging, but hopefully we could come up with some kind of description that at least on average reproduces these properties. It might not be something that we can actually do in 1D at the end of the day, which is why I'm very hopeful for these 3D simulations, but you make a very excellent point.
Okay, we have one question from Brian online, and then, yes, Brian, go ahead.
Thanks, Earl, for the nice talk. I wanted to ask about your proposal about the dark clump in the center of the sun. Because this idea of enhanced metallicity in the core, as you said, is I think an old idea. I guess one of the tests of that was proposed was an enhancement of the CNO cycle neutrinos, and those I believe have now been detected. So I'm wondering, does your model make the same predictions for the CNO neutrino flux, and is that a way to discriminate it from more standard models?
Thanks, Brian, for that question. The CNO neutrino flux, am I going the wrong way? No, I'm not, is not very discriminating. You can see the uncertainties are huge. Like within a few sigma, you say the sun has no CNO at all. And so I don't think that it's super useful for distinguishing solar models personally. Now, of course, this is the aggregated flux. If you decomposed it into the different components, it might be more distinguishing. But yeah, I don't think these measurements are super useful.
I mean, I guess yeah. So I guess my point was, if the metallicity is higher in the core, then the CNO flux is higher. So you're saying your different models aren't distinguishable very much from one where there's not a dark core, but
Yeah, I mean, my
yeah.
feeling is that basically no model would be distinguishable, because if you had a model with no CNO flux at all, for example, you'd say like, okay, that's fine that's like not even statistically significant, you know? Like within 3 sigma, the sun has no CNO flux. Now, of course, there is at least a few CNO neutrinos detected, so that statement was a bit of an exaggeration, but any realistic model cannot be really distinguished with CNO, as far as I know.
Okay, thanks.
Thanks for the cool talk. I was curious about the Thorne Żytkow objects and your prediction that they would have enhanced TIO.
Yes.
From what I understand, the TIO line lists are relatively imprecise. So I was wondering if there would be a similar enhancement in the atomic TI, and whether that might be detectable in the sector as well.
Yeah, I think this TI line is actually for the atomic TI, so that might be the one. I'm not exactly sure why we focused on TIO. It might be the point that that's what distinguished it from a normal red supergiant, but normal red supergiants don't produce any titanium, at least not anywhere near this level. I think our normal red supergiant models, the titanium production was only at the level of noise. And so I think regular titanium is the distinguishing factor.
Awesome, thanks.
So coming back to the dark matter center of the sun, suppose I don't believe that that is what is happening.
Yeah, me either.
But I'd like to understand what changes it is making that bring the astroseismic predictions into better agreement. Can you describe that a little bit more?
Yeah, sure.
You know, at a structural level or something.
Yeah, I'll try that again. So if you have a point mass in the center, this thing's heavy, and so will enhance the gravitational acceleration. And so the net effect is that you transport metals to the core. So you see the metal abundance in the deep interior is much larger. And that's the main effect. And that's because the oscillations are very sensitive to the mu gradient. You can see how that has been modified here. And so if we look at the propagation diagram, okay, you can't actually see it very well. I only plotted one line here. But the main effect is that the P modes, they care about the mean molecular weight. And if you change the distribution, you have metals in the core, you're going to change the spectrum of P mode frequencies. That's the main effect.
Yeah, so could that be produced by changing in the settling rate? Like, what is there a way you can get this metal enhanced? You know, yeah.
Yeah, I mean, I talked to some people who are experts in diffusion and gravitational settling. In fact, my co-author, Matt Kaplan, produces, like, for example, the white dwarfs diffusion tables. And he at least assured me, and he's more expert than I am by far on this topic, that at least in the solar case, the settling rates are really well determined. I could be persuaded. I could pump up the settling and probably get a better solar model just by saying, hey, maybe there's more efficient settling. But he at least argues, because he does molecular dynamics simulations of interiors of stars, that there's no real wiggle room to get these kinds of enhancements.
So maybe just a follow-up question on this. Do you think that this could be explained, for example, by ingestion of planets, early migration and getting a lot of rocky planets in the early sun that then settle into the center on some time scale and then provide a 10 to the minus 3 solar masses of metals that you need?
Yeah, there have been some planet ingestion simulations. I don't think it actually works out with the time scales for the formation, because you need to form the heavy metal core prior to forming planets. And I think that's how it works, at least. We're trying to do improved modeling of the protosun pre-main sequence phase. Again, Evie is working on this. So we might have a better answer for you in a year. But so far, I actually don't think the ingestion scenario helps.